Alright, it's supposed to be Sunday, but it's now Monday, so let's get back to basics. This week, we're going to talk about the watt. Now this is the third time I've recorded this video, so hopefully I've got it down by now. Now, the SI definition of watt talks about it in regards to actual physical work being done, where it says, when an object's velocity is held constant at 1 meter per second against a constant opposing force of 1 newton, the rate at which work is done is 1 watt. That's not really useful for us in the electronics, but we can switch over to in terms of electromagnetism, where 1 watt, oops, that's a terrible W, there we go, is equal to the amount of electrical work performed when a current of 1 amp flows across an electrical potential difference of 1 volt. Now, if we substitute in the values that we're used to seeing in these equations, we can say that power dissipated is equal to current times voltage, P equals IV. And we've seen this, this equation before. We take our current, we multiply it by volts, and we have the amount of watts that we are dissipating in that circuit. What did I do with my eraser? Here I thought I was oh there it is. It's on the floor. Okay. So, we can also find the watt using cat hair all over my eraser. No, we can't find it using cat hair on my eraser. Anyway, there are 2 additional conversions. We can use algebra and substitute in other variables for our formula, but I'll just skip the algebra and move right to the new equations. So our standard equation here is P equals IV. We can also say, and I'll do it with the SI definition units, and then I'll write it down in the units that we typically use, is that 1 watt is equal to 1 times voltage squared over ohms. Or it is also equal to 1 amp squared times ohms. And if we substitute in our normal, everyday, what we're used to seeing, we can say P equals V squared over R. And we can also say it's equal to I squared R. Now this, you've probably heard me use the term I squared R losses before. Now, in general, we only talk about I squared R losses in the electrical field when we're talking about how large voltage over a long run of a conductor generates heat, and you lose power to that heat, which is why power at the outlets is typically, at least here in Canada, it's 120 volts, but it can be anywhere from about 114 to 122-ish, but typically it sits around 117. And that's because of the I squared R losses coming from the transformer to the house. You get a voltage drop and a little bit of heat dissipation across that copper. And as electricians, we have to make allowances for that by making the conductors larger so that they don't dissipate as much energy, because the larger the conductor is, the less resistance it shows to the electricity. And there are various other techniques. You can move the transformer closer and stuff. Anyway, but that's not what you're here to learn. You're here to learn about electronics. Now, I will also refer to I squared R losses in electronics. And I squared R losses, we'll take a quick look at an example here. I'll just bang out a quick circuit here. We'll put in a 6-volt source here, and then we're going to have a resistor, and then we're going to have an LED. Oh, let's try to draw that again. We'll have an LED, there we go. Arrows pointing outwards, denoting that the LED is light emitting. If you put the arrows pointing inwards, it means it's a light-sensitive transistor, which is a different thing. We'll cover those way down the line here. Anyway, so we want to figure out an appropriate resistance for this resistor so that we don't blow up this LED when we put 6 volts across it. And let's say that the forward voltage drop on that LED is 3 volts. Now, when we apply voltage to an LED, it'll only drop 3 volts across it, but it has no internal current regulation, so it will attempt to dissipate as much power as it possibly can. That's why we use a resistor. Now let's say this LED here is rated at 1 watt, which is a very bright LED. So we know we can then calculate what the current for the circuit is going to be. We know that current, or power, is equal to current times voltage. So we can substitute in our 1 watt is equal to current, which is what we need to solve. I'll erase that W because we don't actually need that variable because we know it's 1. And multiply it by the voltage, which in this case is going to be 3 volts across that resistor. So we divide both sides by 3, and we get our current is going to be equal to 333 milliamps, because 1 divided by 3 is 0.333, or 333 milliamps. So now we know the voltage across this resistor is going to be 3 volts, because it's going to have to drop the remaining 3 volts of that 6 volts, and the current through it is going to be 333 milliamps. So then we can use a little bit more math here. We have current, we have voltage, so we can use V equals I R. We have 3 volts. Oops, I don't need to write that V. Go away. There we go. 3 volts equals our current of, 333. 0.333, repeating technically, multiplied by our resistance. Now we divide both sides by 0.333, like so, and we get our resistance is equal to 10 ohms. Now we already know the wattage that's going to be dissipated across that resistor. It's going to be 1 watt. We can find it in all manner of different ways, but just P equals IV, we take the current, multiply it by voltage, and we get 1 watt. Now here's where the I squared R losses come in to electronics. Because, and let me grab my little proto board here that's currently powering my LEDs. These guys right here, these big honkin' resistors, those are 2 watt resistors. They're actually much bigger than they need to be for that circuit. But I had them on hand, so I went ahead and used them. Now, a 1 watt resistor is going to be about 60% the size of that one. And if we dissipate 1 watt through a 1 watt resistor, it's going to heat up to about 100 degrees Celsius. So they get really, really warm. And that's your I squared R losses, because that additional voltage has to be dropped somewhere, and in dropping it, we dissipate power, and the only way to do that in this simple circuit is to dissipate it as heat. So this is a very inefficient circuit. We can make it more efficient, of course, by lowering the voltage to something closer to 3 volts. Like if we made it 3.5 volts, we'd only have to drop a half a volt across that resistor, and all of a sudden we're not dissipating as much wattage across that. But yeah, I've digressed a little too far here, but we've covered now what the watt is, how to calculate it out, where we can find applications for it in a simple circuit. Next week, I will talk about resistance, because we actually haven't talked about that. I won't talk about Ohm's law just yet. We'll just talk about resistance, why materials are resistive, stuff like that. So next week, we'll be talking about, I guess, the ohm, or resistance. And if you haven't already, click this button here to subscribe. YouTube's making me beg for subscribers because of the way they changed the rules, so there's that there. I've got a video that YouTube thinks you'll find interesting based on your watching habits here. This will be the Back to Basics playlist over here. I'll have a link to my Patreon if you want to, send me a couple of bucks a month to help support my channel. And also, there's a little bell button next to the subscribe button down here somewhere. If you click that, you'll get a notification that I've released a new video. Now, as far as releasing new videos, Patreon supporters get these videos 1 day early, or not 1 day early, 1 week early. So if you support me on Patreon, you get to see these a little sooner. Also, feel free to leave any comments, suggestions, questions, and corrections in the comments below. I had somebody very helpfully correct a mistake I made in last week's video, and I made sure I pointed that out in the comments. So thanks so much for watching, and we'll see you next week for the ohm. Bye-bye.